a biostatistician, and I'm not trying to make you one either. Okay, but I have a real simple way that I organize biostats. Here we go. All right, let me count the ways. The ways for what? How to define things. First, key definitions. What is epidemiology? Is the behavior of a disease in a certain population. So just like the way COVID behaved in America was not the way COVID behaved in Russia, was not the way COVID behaved in Africa. Remember, they thought Africa, which has all these poor people, that more of them were going to die. No, there more people died here in America. Because, yeah, they didn't have that crazy pandemic response plan and a Trump leading it.
Okay? And obesity.
Yeah. I know, isn't that crazy? Poorest countries. Because like Nigeria, they thought Nigeria, oh my God, I thought we were going to lose a lot of family members. Because only my immediate family here, but my aunts, uncles still live there. Nobody died. Nobody even caught the damn thing. Nobody got a vaccination, nobody got a pill, nobody got a remdesivir, nobody. It's amazing. So that's why epidemiology, you can only study things in a certain population. You can't say it pertains to everybody. You can never do that. All right, anyway, endemic is the expected annual number of cases. Like here in America, like syphilis, something I reviewed a while ago, 5 cases per 100,000 is the normal expected amount of syphilis. Okay, and then one time it hit 15 cases per 100,000, that's called an epidemic. So an epidemic is when you're 2 standard deviations above the normal expected amount. And pandemic is when the whole world is involved, like COVID. Pandemics occur when a new agent goes from an animal to humans because humans have no antibodies against it. That's why nobody has resisted against it. And so it's going to sweep across the world. Once it's affected enough people, boom, you see, it dies down, just like it did with COVID. Okay, so just so you know what these terms mean. Any questions on these terms? Cool. Key rates. Most rates are per 100,000. I'm sorry, not per 100,000, per 1,000 live births. Just know that. Except crude mortality and maternal mortality per 100,000. All right, birth rate. How many births? How many per 1,000 pregnancies? Fertility rate. How many pregnancies per 1,000 women in childbearing age, 15 to 45? Currently, I close that door now. Yeah. Yes.
Which ones were?
The per 100,000 is crude mortality and maternal mortality.
Oh.
It's usually per 100,000. All the rest of them are usually per 1,000 births. All right, so fertility rate, the key word I use, fertility. Remember, always look for a way to remind yourself of what that term means. Fertility, oh, who's fertile? 15 to 45, okay? Infant mortality rate, an infant is the first 30 days of life. So that's how many children die. Oh, sorry, that's neonatal, sorry, that's the next one, sorry. Infant mortality is from 1 to 12 months. So how many children die between 1 month to 12 months? Infant mortality. Neonatal mortality, how many people died in the first month of life? Now, the number 1 cause of neonatal mortality is still prematurity. RDS, still number 1 cause of that, 60% mortality. Does that make sense? Infant mortality used to be SIDS. Now, I haven't seen an article updated, but if I had to pick an answer, I would say it would be accidents. Because it used to be SIDS first, then accidents. So SIDS is no longer, SIDS is cut down by 90%. Now that we let them sleep on their back of slides, okay? So it makes sense. That means number 2 now is going to rise to number 1, but I have not seen a question to verify that's what they want. All right, anyway, that's neonatal and infant mortality rates. Maternal mortality rates. How many mothers die during the birthing process? That means throughout pregnancy and birthing per 100,000. Maternal mortality is highest after the delivery. Now there's risk throughout the whole delivery. Throughout the whole pregnancy, which is cardiovascular, right? Remember I told you guys when that placenta, 1 million capillaries separate out of a parallel circuit, TPR goes up so fast. Intracerebral hemorrhage still remains number 1 cause of death. So maternal mortality rate, okay, highest amongst Blacks and Hispanics. Crude mortality rate is just, you take the number of people who died over 100,000 population, because it's going to be a humongous number. That's why I say crude. It doesn't really tell you that much, but if you can at least compare, countries, death rate in this country versus this, or states, this state versus this state, but why they're dying, you couldn't tell me based on that number. All right, that's why I say crude. It just gives you an idea, but it does not give you etiology. Case fatality rates, your denominator is the number of people who had the case, and numerator is how many people died from that case. So I remember we had one morning question that did that. You look at people who had E. coli, I can't remember, some bug, gastritis. All right. So case fatality, how many people died versus how many people had the case. Attack rates, how many people got the disease versus how many people, and the denominator is how many people are susceptible to it. Now you only count the people who are susceptible, not the whole population. So case fatality and attack rate are similar, but you got to understand, attack rate is who's actually susceptible. If you're not susceptible, then you don't count. Huh? Incidence is different. Attack rate is just how many people got the disease versus how many people are susceptible to it. I know. That means how many people got exposed to the illness, and then how many people actually got it. No, it's not necessarily incidence. It's just how many people got it over how many people were exposed. So let's say 100 people got exposed, but only 17 people got the disease. Okay, then attack rate is 17%. That's it. That's how you calculate attack rate. But incidence is how many new cases. So that's a whole different calculation. Yes, Andres. Say it again. The amount of people who got the disease, yes, is the amount of people, no. The amount of people who are susceptible are in the denominator. That's attack rate. Right. There's 15 out of that 100 got it. Yeah. So it's just a percentage. Attack rate is a percentage. All right. There are many ways to do a study. How do we set up a study? All right. These are different types of studies. Case study. You write up an interesting case. All residents, all physicians are always encouraged. Please write up, if you got an interesting case, write it up. That way your colleagues can read about it. Okay. A lot of times it'll remind somebody, hey, that sounds like this other case I had, and I couldn't figure out what was going on. And you find out, now you know what it is. You didn't know there was another case in Wisconsin. So a case study is just write up an interesting case. Okay. And you submit it to a journal. Case series. We did a lot of this for COVID. Means I put in some keywords, and every case study, every case study written up with those keywords in it will pop out. This is how you look for trends. All right. Like remember COVID, every week we did another case series. That's how they find out, oh, lungs attack pregnant women. Okay, pregnant women should be vaccinated first. Lungs attack elderly. Oh, yeah, okay, elderly should be vaccinated first. Everybody see that? That's what a case series does. You're looking for trends to make policies, usually government policies, okay? Case series. But that's how we find out things in medicine too. You find out, oh, the most common bug is strep pneumonia. That was a case series, okay? Yeah, case series are a bunch of case studies put together. Yeah, and then you look for trends. Cohort study says a group was involved. If you look forward, that's called prospective. We're going forward. That means we're going to either just watch you for a while, that's called an observational study. Or I'm going to do something to you and see what happens. That's called a clinical trial, which means you're going to intervene somehow, and then let's see what the outcome will be. So prospective studies, it can be observational where you just watch, or you're going to intervene somehow. Okay. Retrospective, so you're looking backwards. Retrospective, so I'm going to look backwards. And then case control is a form of retrospective. I'm looking backwards to find out the exposure to, that caused something. which is hard to do, but it's worth it. Just like they connect the cigarette smoke to cancer. That was a long retrospective study, case control. And mesothelioma, same thing. That's how they figured out. Mesothelioma was like 0.95. That means 95% that if you got exposed to asbestos, you're going to end up with mesothelioma eventually. That's when they said, okay, asbestos must be the cause of mesothelioma. And the companies were made to pitch in $30 billion in lawsuit money. That way, anybody who has mesothelioma can sue for generations to get money for it. Yes.
So case study will be that you're looking at a particular disease, you're looking for the risk factors.
A case control study. Case control study looks backwards to see what was the exposure that caused the disease today. That's why you take a bunch of people who have the case, that's your case, and then I create a control group. Now, what's important about this control group? They have to live in the same area. Because otherwise, how could they be exposed to the same thing if they don't live in the same area? So in case they ask what's the most important thing, is the demographics more than anything else.
But retrospective would be, the cohort will be, get asbestos or any risk factor, we look for cases of that.
Yeah, retrospective cohort says I take a group of people, let's say all the immigrants from China or something like that. And then I'm going to see how many in the past have gotten this disease. Yeah, that's a retrospective study because I'm not looking for the exposure. I'm just looking at who got certain disease. Yep. Case control is you're trying to look back to see what was the exposure that caused the disease. Mabel, is that you?
Yes, sir. Yes,
Okay.
please. What about what did you say about prospective studies, sir? Please, I didn't get it.
Prospective study means you're going forward, Mabel. That's it. You're going to follow them for 5 years, 10 years, 20 years, whatever. The longest running prospective study is Framingham study. Probably about 80 years of data now. Just follow people forward. Okay.
Okay, thank you.
All right, no problem. Clinical trials says I'm going to intervene automatically. That means I'm going to give you a beta blocker and see what happens. Going to give you ACE inhibitor, see what happens. That's what a clinical trial is. Okay. Single blinded means the patient is unaware of what's going on, but the doctor knows. Double blinded, which is the standard, the industry standard. The doctor doesn't know and the patient doesn't know. Why? Because it creates what we call observer bias. If I know who's on the medication, here's what I'm going to ask different questions versus the person who's not on medication. Well, that messes up the whole study because it's not standardized anymore. Whereas if the doctor does not know who's on medication and who's not, guess what? He's going to ask the same questions to everybody because he just thinks he's just taking care of patients. But people behave differently if they know who's on and who's not on medication. So it alleviates observer bias in case they ask you which bias are you eliminating. All right. Meta-analysis is the best study. All right. Means you bring together many, many small studies to create one huge cohort. Now you're increasing the power of your study because you got a humongous cohort. Person who made a fortune out of this, well, built reputation. I'm sure he made money out of it too. Is Cochrane. And Dr. Cochrane, you guys heard of Cochrane reports?
Yeah.
Every year. Huh? I don't think it's the same Cochrane, no, who's a lawyer. This is a doctor. Anyway, but all he does is meta-analysis all year long. But he's the most well-respected because he's the one I see yearly come out with, oh, the most common cause of bacterial pneumonia is stale strep pneumonia. So he pulls together, whatever, how many studies, and now you got about 500,000 cases. That way you can believe whatever the results are, okay? That's what meta-analysis gives you such a huge cohort. The power is so strong that you can believe whatever the results are. So meta-analysis. So the key is you got to put in some key words that each study has to satisfy. That means if you're doing a study about pneumonia in kids, you can't just say people with pneumonia. You don't know how many are kids, you don't know how many adults. And that would be illegitimate meta-analysis. All right. Cross-sectional is when you randomly pick people for a study. Remember we saw that in one of our morning questions? If you just stand out in a corner and have people fill out a questionnaire, that's a cross-sectional study. Cross-sectional studies are done just to find out the incidence or prevalence of a problem. Politicians use this all the time. So if I'm a new senator, a new representative, I want to know what's going on in my district. They hire some teenagers to stand up on the corners in downtown Chicago. Just say, would you like to fill out this questionnaire, sir, about blank? Well, then if you fill it out, then you say, oh my God, hey, a lot of people said there's no garbage pickup going on the west side. See, now he's a politician. He's got to figure out why is there no garbage pickup on the west side? So cross-section picks up incidents and prevalence, but not etiology. You have no idea why it's going on. You're just detecting things. So it's the worst type of study. For politics, it's a great study. For medicine, no, because there's no criteria for entry. Anybody can do it. Okay? Cross-sectional study. Any questions on that? All right. Is the only study with random random population selection. So cross-sectional studies. Okay? All right. Now, whenever you do a cross-sectional study, you run into two biases. Responder, no selection. That'll come up later. You can have a selection bias only because there's no entry criteria. Yeah, so that's why they don't even talk about that kind of bias, because we already know it's biased already from the beginning. But anyway, there's a responder bias. What's a responder bias? The people who actually take time out of their day to stop and fill out those questionnaires means that it's something important to them to have to say to the politician. See, so you actually get a skewed view. It's not a random view as we thought. Because, if I'm on my way to somewhere, but I'm going to stop for 15 minutes to fill out this questionnaire you just gave me, it means I got something I got to tell you. I'm pissed. I can't pick up the garbage in my neighborhood, and I'm trying. So they found responder bias. Okay? And then there's non-responder bias. Maybe you don't want to fill them out. That's because non-responders don't give a damn about it. But either way, it's not a random sample anymore, like we thought. Anyway, those are two biases associated with that one. Longitudinal. So we're going to follow you for a while. 5-year study, 10-year study, 20-year study, whatever. But that's usually set ahead of time. Yeah, usually a prospective study, and you didn't state how long you're going to follow them. Now, things like cancer and heart disease, you got to follow them for minimum 10 years before you make any conclusions. But usually we follow them for like 30, 40 years. But you cannot make any conclusions for at least 10 years. Otherwise, what you got is what we call lead time bias. What's the lead time bias? Early on, there is no disease. So you think you're making a difference because you're doing something. No, they just don't have disease yet. That's why you set the timing based on what disease you're looking for. Okay, whereas when talking about a rash, well, hell, you get a rash every day, so you don't need a long-term study for that. But longitudinal, all right? Watch out for lead time bias, okay? What? No, there's latent period and there's lead time. Latent period bias says, remember we ran into one of those in the morning, that early on, there's only a small amount of disease, so you can only make a small amount of difference. Most of the disease is later, so you can talk about that if you want to, but I just happen to mention lead time is the biggest bias you create in longitudinal studies, okay? But
Excuse me.
Wait a minute, Mabel. So length time, I want to make sure everybody understands the difference because they sound alike, but they're not the same thing. Lead time says you didn't wait long enough to lead up to the disease. That means like the first 5 years, there is no heart disease. If I raise your cholesterol today, you don't get a heart attack in 5 years. That's why if you did a 3-year study, worthless. Because you tell me, yeah, everybody's still alive because of my drug. No, they aren't. They just don't have any heart disease yet. Okay, that's lead time bias. Had you followed for 10, 15 years, you would have seen problems. Length time. I saw latent period is another one. As long as I said it, let me talk about that one. Latent period bias. Latent period bias says in the first time period, there's hardly any disease, so you can only make a small amount of difference. And it's usually not significant. But in the second time period, there's a whole lot more disease, and so you make a bigger difference. Okay? Whereas, what was the other one you asked? Late time? That's what you asked? Yeah, latent period bias. Latent period bias says some diseases are just slow in their development. So it's out of because it's slow in their development, not because there's no disease, but because they're indolent, like prostate cancer can be indolent for decades before you actually get any symptoms from it. Exactly. Delayed onset versus slow progression. That's a good way to put it. Nadeem?
Like they had a question, they said like a new test that detected earlier,
Mhm.
right? Would that be lead time affect lead time?
Lead time. It just means you did a short, the way I like to look at it, make it easier. Short-term study on a long-term disease.
Okay.
Yeah, I don't even care what test they're using. Everybody likes to define it based on tests. I said, for me, it's easier if you just say, you're doing a short-term study on a long-term disease, I can catch right away in the beginning. Because they're telling me something about cancer, and I said, 3-year study? No way. You can't even see cancer in 3 years. I already know it's a lead time bias that they want. All right, observational says I'm not going to intervene. This is a Framingham study. All they do is just observe 80 years worth of data right now. Now, they're in the 4th generation of people, you can opt out. That's because we know the consequence of a lot of diseases now. So I don't want to be left alone to die. Okay, but that's what they did. Families actually signed up and say, okay, fine, you can just watch. And some brave families. First, prospective studies choose a sample population, divide into 2 groups based on presence or absence of a risk factor. Then you follow the patients over time and you measure incidence and prevalence. What does incidence read? And prevalence is total cases. Okay. And of course, it's more expensive because you got to keep track of them. So you hire a bunch of nurses who are going to be calling periodically, making sure everything's okay. That's how you keep contact with them. That way, if they're going to move, they'll tell you, yeah, we're going to move it to Arizona next month. And that way we know where they're going to be moving. Otherwise, you're going to lose them to follow up. Okay. And that creates the selection bias because people who tend to drop out are the ones in the treatment group. Now it's not balanced anymore. Okay. So prospective studies. Retrospective studies, samples are chosen after the fact based on presence or absence of a problem and then information gathered for possible risk factors. Specifically for case control, because you're looking for the, what is the risk factor? What is the exposure that causes disease? Case series, good for rare diseases. That way then looking through the literature for as many cases as you can find. All you gotta do is put in some keywords and the computer will spit out all the cases in literature for you. Cross-sectional studies. Remember I told you we always do everything twice, just so everybody remembers. We talk about it, then I go through it again for you. All right, cross-sectional study is a prevalence or incidence survey, randomly chosen people, no entry criteria. Okay, notice I highlighted no conclusions can be made. Most times when I see that question, they always put in a conclusion. That's always wrong. I don't care what the conclusion is. You cannot conclude anything. Because remember, there's no entry criteria, there's no standardization that was done. You cannot make a conclusion. You can only say, oh, incidence or prevalence or problem exists. How do you evaluate a test now? Measurements of value, sensitivity. Lauren, what's the equation for sensitivity? Don't give me letters, man. Just tell me what it means. Okay, hey, all right. Let me tell you, it's true positive. If I'm sensitive to your needs, that means I detect your needs. So this detects a disease, true positive. Over true positive plus false negative. And that's because false negatives were supposed to be positive. Sensitivity. Specificity rules out normal people. So it starts with true negatives. So again, by speaking it out, I remind myself of the equation. True negatives, I'm trying to detect normal people. They truly don't have the disease. True negatives over true negatives plus false positives. Specificity. Any questions? Positive predictive value. How sure are you your positive is really positive? Positive and negative predictive value are questions asked after I give you the results. If you ask me about the test before I do the test, then it's sensitivity and specificity. How sure are you I'm having a heart attack? Well, let me do an EKG then. That's sensitivity. How sure are you I'm not having a heart attack? Okay, with specificity. But now I run the test and I give them the EKG and say, this, see, it's certainly having a heart attack. Well, are you really sure about that? That's positive predictive value. How are you sure that positive is really positive? So, positive predictive value, true positives, over all the positives. True positives plus false positives. And negative predicted value, true negatives over all negatives. True negatives plus false negatives.
Can you go over the wording of?
The negative predicted value says, how sure are you the negative test is really negative? So when you write it out, they say, you gave the patient a negative biopsy. And the patient says, well, how sure are you that I'm not really sick? That's how sure are you that negative is really negative? That's negative predicted value, because they're questioning it after you've given them the results. Okay. Relative risk says, what is your risk compared to the general population? The general population risk is 1. Comes from that 1 to 3% I've given you. It's just that 1 is easier for doctors to remember. 1. So that means, Melissa, if you say your relative risk is 1.7, they'll ask you how do you interpret that? How would you interpret it? What's that? You're what? Yeah, you're more at risk, but how do you interpret the number? No, not 1.7. So if you say your relative is 1.7, that means you're 1.7 times more risk than the general person. But the real interpretation is you have 70% extra risk. 7.7 is 70% of 1. Okay, and that's what they want. That's an answer. That you got 70% extra risk. Okay, compared to the general population. All right, now if your relative risk is 5, then that means you're 5 times the risk of the general population. I just gave you a number, 1.7.
Oh, no.
0.7 is 70% of 1. So you have 70% extra risk after being exposed to a blank. Yeah.
So if it was, if your relative risk is 1.7, you're 0.7 times as much. Same.
You have 0.7 extra risk. Yeah.
But if it's 5, so you had subtracted it from, subtracted the 1 because that was the general.
No, you're about to do attributed risk, which is the next thing I'm going to go. Relative risk is just what is your risk compared to general population. So 5 says you're 5 times likely to get the disease after this exposure than the general population.
So why is 1.7 not?
I did say that. I said you're 1.7 times more likely to get something after exposure. But that means there's 70% extra risk after the exposure. You can say it 2 different ways. That's it. Or like 5 is that's 500%. So that means you got 400% extra risk. Yeah, you can say it either way you want. What's the extra risk, or how much more likely am I to get it after the exposure? Okay. Attributable risk, it says how much of that risk is attributable to the exposure. Well, the risk of being part of the population is already 1. So all I do is subtract 1. So if you tell me relative risk is 5, I subtract 1. That means 4 of the 5 is attributable. That means 80% is the attributable risk. Oops. Oh, okay. I was about to look for it. I knew somebody's hand was up over here. All right, what is it? Okay. Yeah, rapid COVID test is to be sensitive. Anytime you're screening, okay? Well, let me finish these and I'll go back up and show you ways to manipulate this. All right, so relative risk, attributed risk, any questions on that?
Yeah, yes, sir. I have questions, sir.
Wait a minute, baby, wait a minute. All right, attributable risk says how much of the risk that you calculated is attributable to the exposure, because 1 is already the risk of being part of the population. Okay, so if you say 5, and then I subtract 1, that means 4 of the 5 is attributable to the exposure. Because 1 is just by chance. Remember, you have a 1 to 3% chance of getting lung cancer without being a smoker. So there's always risk for being part of the population, period. So that's why you always have to subtract 1. I find it much easier because I know students can subtract 1, I hope. Okay, subtract 1, put it over the total, there it is. It's much easier, folks. It's trying to remember A over this, over A. I don't do any of that. Okay, subtract 1. I get the same answer they get. Okay? All right, and an odds ratio, you set up your 4 quadrants. Remember? A, B, C, D, right? A, B, C, D. Odds ratio, I put an X. A times D over B times C. So I just think of making an X. See that? Easy to remember. Visual memory now. Instead of trying to remember what the book told me. All right? So odds ratio just has to do with retrospective studies. That means what are the odds that what I'm looking at is the exposure? That's it. Just what are the odds? Like I told you, the mesothelioma was like 0.95. That means there's a 95% chance that is exposure. That's pretty high. That's why they said, okay, the company's got to pay up. Okay. So anything above 0.5 is strong. Below 0.5, okay, weak. All right, now going back up here, sensitivity. When do you want the most sensitivity applied? Number 1, when you're screening the general public. Why screen people when you don't detect the disease? Wouldn't make any sense. Whenever you're screening people, you want the highest sensitivity. So they'll say, well, you want to screen the public for whatever. They say, well, which one of these tests would you use? All you do is look for the one with the highest sensitivity. That's it. That's number 1. Number 2, when you're screening children. Why? Because if you miss one case, that's a lot of years of life lost. So screening babies or children, we don't want to be wrong even one time. So you want the most sensitive test done because a lot of years of life is lost if we miss one. And number 3, if the disease is deadly, because you don't want to miss one case again. Does that make sense to everybody? It's got to make sense for you to remember now. I always try to kind of visualize, why does that make sense? Ah, I got it now. Then I can visualize and see it. So when do you want the most sensitive test is those 3 reasons. All right, Mabel, your question.
Sir, please, when do we want most sensitive test, please?
Good Lord. I told you there's something wrong with that, her sound system. I say something 5 seconds later. She asked me the same thing I just said. Mabel, I don't know. You got to work on that sound system.
Please, I just have
what sensitivity is.
1 week to go.
Listen up, Mabel. I'm going to give it to you one more time. So I don't know if it's that mic or you're not listening, but just so you get it, because listen carefully. Sensitivity, you need it to be the highest. Number 1, when you're screening the general public. Number 2, when you're screening children. And number 3, when you're screening for deadly diseases. You want the highest sensitivity. And then second, specific tests are done after sensitive tests. Remember, just like HIV, you do the sensitive, then you do specific. Because specific, you rule out normal people. Because you're going to get some false positives on your sensitive. Okay? But you rule them out with specific tests.
Okay. That's not my question, sir.
What's that?
Please, can you clear me on relative risk and attributed risk, sir, please? I didn't get it.
Good Lord. Did you get the sensitive test?
No, I didn't get any of them. I'm not the only one that's having this issue. Some people are having this issue.
No, you're the only one, Mabel. I think there's something wrong with your system because you always ask me right after I say it. So that's how I know you're not hearing it. I don't know why. Okay? Relative risk. All right. Is there anybody else in the online who did not hear relative risk and attributed risk? What they say? Let me see what it says. It says having 1% chance of getting a disease belt exposure. Yeah, but she's saying that she's not the only one. Anybody else not saying hearing this? Why do you subtract 1? Remember, 1 is a chance of being of chance alone, chance of anything happening. Is 1 to 3%, but they use 1 because it's easy for doctors to remember. Okay. All right, Mabel, listen up.
Okay, sir.
All right, Mabel, here it is. Listen very carefully. Relative risk is how much more is your risk than the general population after a certain exposure. That means the risk of the chance of getting lung cancer is 1 to 3%. That's by chance alone. But if you're a smoker, now it's like 8 times that. That means you have 8 times the risk if you smoke to get lung cancer. That means 8 times more than the general population. That's what relative risk is. You understand that, Mabel?
Yeah, yes, sir, I do.
Okay, anybody else online not understand what I just said? Make sure you ask when I'm doing it at that time. All right, attributable risk, all you do is subtract 1 from your relative risk. And then what's left is your attributable risk. That's the easiest route to calculate it. So you don't have to try to remember complex equations. I don't use any of those equations. And then odds ratio, I just showed you, set up your boxes A, B, C, and D, and just make an X. A times D over B times C, that's your odds ratio. All it is what are the odds, and what I'm looking at right now is the exposure that causes diseases. You understand that, Mabel?
Yeah, gracias.
All right. So sensitivity, specificity, any question on any of these terms? Okay. All right. Yes, sir. AD, yeah, AD over BC. That equals odds ratio. Okay, what amount did you find? Years in AD are larger than years in BC before Christ. Oh man, I never thought about that. Oh, and that's why then you set up a ratio, which that means it's much more likely you're going to get the disease because it is equivalent. Oh, my man, good. I like that one. Very good. All right, Ryan Ford, you have a question?
Yeah, so quick question. So sensitivity rules out of disease and specificity rules in a disease.
Correct.
Okay.
Yeah, so sensitive, the best way I like to say it, sensitive picks up the disease, and sensitivity, I said specificity rules out normal people. Yeah, but you are right. All right, measurements of value. Test reliability or precision. Says, can you give me the same result with the same blood? That means if I run a certain test on your blood 3 times, I should get the same number. If I don't, then it's not precise. So precision or reliability says you get the same number from the same blood sample from the same person. Well, you and I know certain machines give you several different numbers. Okay, same blood, but that's why there's no so precise. Now, this is how investigators attack each other. Okay, so let's say you use the X503 for your BUN determination, and somebody says, hey, man, you didn't know about the B102? That's doing the market, man. It's a lot better. All of a sudden, the study you just did is worthless because there's a better machine that will give you more reliable levels of BUN. So that's why then they're the ones who keep track of, what machines are reliable and what's not. Okay, but you need to know an interpretation. Okay, all right. So that's reliability and precision. Accuracy is when they give you the gold standard. So they'll tell you the gold standard shows, and then you compare it to the numbers you're getting. If you're far off, then it's not accurate either. If you're real close, then it is accurate. So you can speak to precision, you can speak to accuracy. But accuracy and validity is only if they tell you what the gold standard is. If they don't, you cannot speak to it. Any questions on that? You understand, Mabel?
I do.
Okay. So confidence interval. The confidence interval says, how confident are you that your number represents 95% of the population? Mabel, how many standard deviations is 95%?
95% is that's the topmost. That's the second. So is it 1 3 or something? 3 to 1?
No. All right, Sabu, how many standard deviations is 95%? And Maria, it's 2. Remember, say 1 is 68, 2 is 95, 3 is 99.6. All right, so confidence interval, again, interpretation, if that's what they're asking, says how confident are you that that number represents 95% of people in the population? If so, both the confidence intervals got to be on the same number, on the same side of 1 as your confidence, as your relative risk or odds ratio. So let's say you say your confidence interval is, relative risk is 1.7. Confidence interval is 0.9 to 0.98. Well, 1.7 is above 1, and your confidence interval numbers are below 1. That's an invalid study. Your confidence interval has to be on the same side of 1 as your relative risk. They have to. Because remember, you cannot go across 1. It means the study was messed up. Something went wrong. So if your relative risk is above 1, both the confidence interval numbers gotta be above 1. Then I don't care what the number is after that. If your relative risk is below 1, let's say 0.95, then I need both confidence interval numbers to be below 1 as well. Then it's a legitimate study. And then if they are, then you give it a significant p-value. What's the p-value? P-value, right? Remember, 0.05 or less. What is a p-value? Pearson coefficient. 0.05 or less says your finding is not only valid, but it's also significant. But how significant is it? Watch, listen carefully. It means there's less than 5% chance that this is a random finding. That's what a p-value means. What is the chance that your finding is a random finding, which means it's not real at all? Less than 5% chance. That means more than 95% chance you're actually right. That's why we say we'll accept it. That's why it's so important for the p-value to be less than 0.05, because that means you are more than 95% chance that your finding is real. Yes, sir. Yeah, we're going to get to Nolan. I'll turn it about in a second. Yes.
If you want to, numbers again for the confidence. If you have one.
Your confidence interval, if your relative risk is above 1, your confidence interval numbers both got to be above 1. If your relative risk is below 1, both your confidence interval numbers got to be below 1. Yeah. And if they are, then it was a significant study. I mean, significant finding. But how sure are you? Then we assign a p-value. That means the p-value is going to be significant too. That means less than 0.05. Okay. So if the p-value is less than 0.01, that's even better, isn't it? That means now I'm more than 99% sure that I'm right. Okay. So the lower the Pearson coefficient, the more confident you are that your finding is real. Because less of a chance of being a random finding. You understand, Halima? It's called Pearson, Dr. Pearson. That's what the P stands for, Pearson. You understand, Halima? All right, measurements of value. Measurements of risk, absolute risk. This is relative risk that we just talked about. I'm just defining it for you. So attributed risk says how much is due to the exposure. Relative risk says what is your risk after exposure compared to the general population. And then odds ratio says what are the odds that what you're looking at in the past is the actual exposure. Okay. Any questions on that? Okay. What if a study is not set up correctly? Then you end up with a whole lot of biases. Now, I'm trying to mention different biases as we go, but I'm just going to go through some common ones. Selection bias. Yes.
Let's say RR minus 1.
Yeah, relative risk minus 1, which is the risk of being in a population. R minus 1.
That's the same thing as being
That's attributed risk you're trying to find. R minus 1 over relative risk equals attributed risk. Yeah, so 4, if the risk was 5, you say 4 minus 1 over the 5. There it is, 80% attributed risk.
I'm trying to understand where they say that the C minus this.
I have no idea about those letters you're talking about. I don't use the letters, man. I try to understand what they're talking about, so I don't have to remember all these letters. That way, once they give me the numbers, I just subtract 1, put it over the total. There it is. Yeah, I get the same number they get. Instead of trying to remember C's and D's and A's, I get all confused, man. And I know a lot of you guys do too, because you're trying to memorize letters. Try to understand what they mean. All right, selection bias, Zena, you brought this up earlier. A selection bias happens for one of 2 reasons. Number 1, you don't have well-stated entry criteria, so the wrong people are in the study. Let's say I want to do a study on subarachnoid hemorrhage, right? Thunderclap headache. And what's your entry criteria? Severe headache. Man, I get severe headache from a URI. So does that mean I had a subarachnoid hemorrhage? No, it doesn't. That's why you got to define it much better than that. That's a selection bias. You got the wrong people in your study. And number two, if there's a high dropout rate, it unbalances the treatment group and the control group. Selection bias. Second, measurement bias is human error. If I gave 5 of you some numbers to add, I get at least 4 different numbers. That's just human error. People don't do math very well. How do you get around measurement bias? Use a computer. Seriously, that's why the computers do all the calculations in your study. Okay? Because we know if you let humans do it, you're going to make a lot of errors. Most people can't even balance a checkbook. I'm one of them, so no problem there. I finally give up on checkbooks. Now I just write the check I wrote. I ain't trying to balance it anymore. At the end of the month, I said, okay, yeah, that's about how much I got left. They can rip me off. I don't even No, I estimate how much I should have left after the checks come through. All right, but anyway, measurement bias is just human error, folks. Can't avoid it. Observer experiment expectancy. Remember observer bias I already talked about? Is when an observer knows who's on the medication, who's not, he's going to act differently. Experiment says if I'm, let's say if I work for the company, then I want the results to be positive. Guess what? I'm going to steer it in that direction because I expect it to be a good outcome or a bad outcome. That's still a type of observer bias, just so you know. Okay? Latent time bias, we just went through that. Okay? Versus lead time bias. Okay? Short-term study on a long-term disease. And then recall bias. Oh, I forgot my S on this one. So recall bias is for retrospective studies. Just by chance, people don't remember things. That means you're more likely to underestimate things when you do a retrospective study. Recall bias. People just don't remember what they did a week ago, a year ago, and so it underestimates. And then Hawthorne bias. Hawthorne bias is when you're afraid of what people will think about your behavior. Or if you're aware that you're being watched, you act differently. Being watched affects how you behave, Hawthorne, how you behave. And that could be the patient or it could be the doctor, it doesn't matter. All right, so if the doctor is supposed to do whatever workup on the patient, if there's a camera watching, Hawthorne bias. Because now he knows somebody's watching. They act totally differently. Versus let the doctor just do his own practice. Then you can come in and see what did he do. Then you can say, well, he forgot to do this, I forgot to do that. But if there's a camera watching, oh my God, they start acting differently. That's when they get nervous. That's normal. All right, same thing with the patients. If they know they're being watched, Hawthorne. Yes.
Both observer bias, Hawthorne bias would be fixed by double blinding.
By double blinding. Yeah, that way nobody knows who's on anything. So Hawthorne bias. Oh, there was one more thing I wanted to say about Hawthorne. Oh, subconscious is telling me something. Hawthorne. Reminds me of something. Hawthorne. How you be? Oh, there it is. Okay. There was a study being done on the effects of sleep on your daily performance. The study hadn't even started yet. Okay, so they recruited people. All right, but the people didn't know what was going on. Just in a short period of time before the people was even randomized, the people who were recruited to be in a study were sleeping more. Why? Because they know there's a sleep study that they're supposed to be participating in. See, Hawthorne. See, that skews the whole study. Okay? Because you want people to behave normally. Sleep when everybody wants to sleep, don't sleep when everybody wants to sleep. Because that's how we didn't figure out what's going on. But if everybody starts acting like, oh, we better go to sleep on time because they're watching us now. See, that's Hawthorne thing. Okay, and that's the one I see a lot in study questions. You know, it's affected the study, and yet you haven't even started yet. It's just because they know you're looking for blank. Okay, all right, Hawthorne. Bergson bias is when you do studies in the hospital setting, then everything's skewed because only the sickest people are in the hospital. Remember, that's why they always do double-blind, randomized, multi-center trials. You can't have them all be in the hospital. Okay, we want to see them out in the outpatient area too. Okay, so Bergson's. Mabel, do you have a question? I see your hand is up.
Please, I want to, have you touched on confounding bias?
No, I haven't gotten there yet.
Oh, thank you, dear.
Okay. All right, there it is. So confounding bias, okay, comes from the word confusing. Confounding bias is elimination of anything that could confuse the outcome. The way you do that is have everything the same on both sides, treatment group, placebo group, okay? Everything the same on both sides except the one factor that you're studying. What does that mean? Have the same number of women on both sides, so female gender is not the issue. Same number of men on both sides, so male gender is not the issue. Have the same number of adults, so adults is not the issue. Have the same number of children, whatever. You try to make everything equal. And that's why whenever you read about a study, that process is in the first page. They show you what the treatment group is and the placebo group, and they put a star on anything that was not balanced, because you're not sure if that plays confounding bias or not. So let's say you got too many blonde-haired people on one side. Well, we don't know if blonde hair has anything to do with the study, but you have to put a star by it to so that the person reading the article recognizes, well, you can look at it and say, yeah, probably no big deal. But let's say you're doing a study on DVTs and you put all the women on one side. Oh, now I'm going to fight your study. I'm like, wait a minute, how you can put all the women on one side when female gender is already a risk factor for DVT? That means you messed up your study from day one. That's called effect modification. It's a type of confounding bias. When something's already been proven in the literature, not in your mind now, in the literature, and yet you didn't randomize it. That's called effect modification. Another good one, you're doing prostate cancer studies, and you put all the black men on one side, all the white men on one side. Black men get more prostate cancer. That's it, you already messed up the study from day one. That's effect modification. It's a type of confounding. That's correct. That's why we let computers randomize it, not humans. Because think about it, a human being is not going to keep track of, okay, you're a male of average height with this and that, blonde hair, brown eyes, and keep track of all of that and make sure this side has all the same thing too. Only a computer can do that for you. So that's why all that randomization is done by computer. The other reason for that is so that way doctors cannot play favorites. That's correct. Selection bias and confounding bias is eliminated by computer randomization. Okay? Huh? What about, yeah, you can do risk stratification. Yeah, again, it's done. Let a computer do it. That way it's done precisely. And then the computer can tell you when they do look at the two groups, oh, we're a little bit off on this group, a little bit off on this, and tell you everything that you're a little off on. As long as it doesn't impact the study, no big deal. But yeah, you try to see, make sure, can this actually impact the study? If it can, you got to randomize it a different way. Okay? All right. Clinical trials. Remember, I explained this to you earlier today. Just remind you again. Preclinical is when you test animals. Phase 1, testing safety in humans, volunteers. Phase 2, testing patient volunteers who have the disease. Okay? And phase 3, either you prove superior to what's already being used out there, that's called superiority trial, or prove that you're just as good as anything else being used out there, that's called non-inferiority trial. You can prove either one. Remember, if you do superiority, that's a huge payoff for a drug company. Because if they're right, every doctor has to switch immediately. Because it would be unethical to keep using the old drug. Okay? But if they do not prove it in that study, they lose all the investments they made in that drug. And the average drug now is costing almost $200 million before you can bring it to market. So a company has to think real hard before they say, are we willing to lose $200 million if we're wrong? Because if you don't prove superiority, that's it. X goes across, that's it, next. Non-inferiority just says, I'm just as good as anything. Beta blockers, calcium, you just want to compete for the market, that's all. Okay? And phase 4 is post-marketing studies. Summarize your data, almost done. Mean is average. Take the number, take all the numbers, divide by the number of numbers. That's a mean. Median, middle number. It's easy when you got odd number, like 5 fingers, the middle finger is the median. But if you got 6 numbers, you got to take the 2 middle ones and add them and divide in half. That's your median number. Mode is a number that comes up the most. Did you know there's a mode calculated for every medical school in the world? Yes, there's a mode. The mode changes the least. Everybody understand that? The mode changes. Let's say if you and I are in the same class, you can get 80% of the test. I can get 80% of the test, but it should not be the same questions. If there is, that's how they catch us cheating. Everybody understand what I just said? What's the mode? The number that shows up the most. Everybody understand? Okay, so if your mode changes, that means more people got the exact same number again with the same questions. There's no way suddenly 18 people in the same class got the same percentage by getting the same questions right. The chance of that is so slim. That's how they come and raid your school. Somebody's cheating in this school. Folks, that's how they found a bunch of Caribbean schools cheating. Let me tell you one big one. This happened in Puerto Rico. There's one they call Rivalida. Some of you guys know what I'm talking about, right? This is a test for Puerto Rican physicians to certify, right? Well, somebody obviously got hold of the questions and started circulating around and selling it to other students because so many people were failing. And so they ran a test 1 year, and all of a sudden this mode changed. They said, wait a minute, there's some cheating going on. You know how they caught him? The next year, or the next time the test was offered, they changed the whole test without telling anybody they changed the whole test. Everybody flunked. I think 2 people passed. That was it. Out of almost 1,000. See? There's a mode for everybody. All right? A mode will get you busted. All right? So, like if you guarantee somebody, people that they'll pass, they already know you're cheating. You can't guarantee anybody can pass. All right, you can only do everything you can to help somebody pass, but you can't guarantee it. There was a guy who was running a program called an Optimum program. Anybody heard about that one? All right, Optimum program. This guy paid students to sign up for the test, copy down as many questions as they can remember, and then bring it to him. He had over 5,000 questions that they remembered. Okay, and he paid them for it. So he was advertising on the internet, will guarantee you'll pass. Because he would give you the 5,000 questions, which means the chance some of these questions will show up is very good. And students were passing, but they were getting the same questions right. And the mode changed. It's okay, there's some cheating going on. They started tracking it. Come on, computers can track anything. And before they knew it, boom, the Optimum program. They realized most of these students went to Optimum program. They raided the man's office. Now he got wind they were coming because he took off. Back to his home country, wherever that was. He took off. He left the students there. I'm serious. And he left the computers there. They went into computers, saw all the names of every student who had gone out to the program, nullified everybody's grade. Yeah. The way I found out, because I had 2 students who came here. I mean, they were already in residency. Imagine you're in residency and you're told you got to go back and pass step 1 again because your score is no good. Yeah. I mean, if that doesn't create sense, I don't know what. But luckily, the 2 we had, we got a vote to pass. But that's how I found out about the whole story. But that's just so you know, every school, and there's been a couple of Caribbean schools, I'm not going to name them, because some of you might be from there, they got busted cheating, and that's how they caught them. Okay, yes.
That's why they make you do the survey after the exam.
That's why you do a survey. Yeah, which test centers you go to? Oh yeah, that's how they track everything. And whenever the mode changes, they say there's some cheating going on in this center, or it's cheating going on in this school, and they send somebody over there to figure it out. And then everybody involved, grades nullified. Anyway, so please, all right, anyway, positive skew. If mean, median, and mode are equal, then you get a perfect bell-shaped curve. If positive skew, that means the mean is greater than the median. And if you got negative skew, that means mean is less than median. So positive skew says your arm is to the right. That means you're pulling in some of these high numbers. Negative skew, your arm is, instead of tail to the left, sorry, I said arm. I was doing my arm, but it's really tail. Tail to the left. That means you're pulling in some of these low numbers. And that's why the mean is less than median.
So positive when someone got like perfect score.
Yeah, exactly. When somebody gets a perfect score and everybody else is averaging, 70 percentile. They're like, wait a minute, how come this guy got 99 percentile, everybody else got in the 70s? And then they're gonna check him out and see, how did you do that? Yeah. I mean, they track everything, folks. Computers keep track of everything that's going on. But he says that's how they find, because I always hear every now and then when they bust another group who was cheating. Okay. I remember there was a bunch of students in India. This was well known. All the news was over the news. They were able to hack into the database and get the questions. I'm serious. And all of a sudden, everybody scored a perfect 260. Every one of them. Like, wait a minute. India got a 260 now. I'm serious. As I'm standing right here. I'm hearing about it every hospital. Oh yeah, we took these students, they got 260. And I'm saying, how did everybody get 260 all of a sudden? I never heard that many students get, and everybody got the same number, 260. And I said, okay, well, anyway, this was before the FBI did their investigation. Of course, they found it. They got the guys who were selling it. All of a sudden, all of them started failing. All right, because what they found was they took them, the residencies took them, and then when this was going around, they told the administrators to check these students and ask them questions on teacher rounds. The student had no idea. It's like, well, how you get 260 and you don't know radionuclide for glycolysis? I mean, it didn't make any sense. I'm serious. They caught them. They just did not know the information. They said, there's no way you can score 260 and you don't know any of this basic stuff. I'm serious. Anyway, let me just finish up. Only a few more slides. Let's go. So here's the bell-shaped curve that I'm talking about. Positive skew, negative skew. They'll describe it based on mean and median. That's why I gave you that as well. All right, statistically setting up a study. Here come that null stuff you were asking about. Statistical inference. First, you define the research question. My question, beta blockers decrease mortality after an MI. So I'm going to define the question. Then I define the hypothesis. Beta blockers do not decrease mortality after an MI. Everybody understand? I'm going to say no. That means I'm going to say no to whatever I'm doing. That means I'm out to prove myself false. You see? Then I define the alternative hypothesis. Means if I prove myself false, that means beta blockers do make a difference in mortality after an MI. Okay? That means you drop the null hypothesis and pick up the alternative hypothesis. Okay? P-value, as I told you, significant is less than 0.05. It means what are the chances that your finding is still a random finding? Less than 5% chance. We say we'll accept it. Because when you flip it, there's more than 95% chance your finding is real. Types of errors.
So,
Type 1 error.
Oh,
hang on, maybe I'm almost done. Let me just finish up. Then you can ask your question. So type 1 error is an alpha error. All right. That means a chance of rejecting the null hypothesis. That means what's the chance that you're finding the study is really not good? Or you say that there is a difference, but there really isn't. That's a study problem. That means the way you set up the study was all wrong, and that's why you found no real difference. So alpha error, the chance that you say there's a difference, but there isn't. And a beta error or type 2 error, the chance you say there is no difference, but there really is. That's my misinterpretation. That's called human error. And therefore, when you subtract beta, human error, from 1, that's the true power. So that's the way I remember it. You're eliminating human error. What's left is the real power of your study.
So what was the alpha error again?
Alpha error is a chance you said that there's a difference, but there really isn't. That means that's a systemic error. That means the way you set up your study was all wrong.
Okay,
Because
thank
you
you.
said there was a difference, but there really isn't. Okay? And then beta or type 2 error, you say there really is no difference. And then somebody looks over the numbers and say, oh, no, there is a difference. Okay, let me tell you one, most recently, was estrogen replacement therapy. Remember, at one time they said, oh, estrogen replacement therapy is deadly. Don't use it, don't use it, don't use it. Remember? We were told, no more estrogen replacement therapy. But when somebody took a look at all the numbers, they found, no, it's not that you should never take it. They found a decreased mortality for 10 years before menopause and up to 10 years after menopause. So it's a window. 7 studies. But the first guy who interpreted it said, oh my God, never use estrogen replacement therapy in women. That's not what the results showed. That was his misinterpretation. And of course, they went back and said that. Yeah, yeah, so type 1 error, you say there's a difference, but there really isn't. Type B error, you say there's no difference, but there really is. And statistical testing, t-test, T is for 2. You're comparing any 2 sets of data. T is for 2. Compare any 2 sets of data. Just remember T for 2, that's how I remember it. Okay? Matched pair t-test is the same person before and after. Like you took a test the first day you were here, and you take a test this weekend, that's matched pair t-test. That means I look at your numbers to see if you're progressing. Okay? So remember, you guys are supposed to take that test this weekend too. Just to remind you, right? So chi-square. Oh, well, to connect to that, analysis of variance is when you're comparing 3 or more sets of data. They're related. So T is for any two, but if they say 3 or more, the answer is ANOVA. Now it's a variance. Then if you want to look for a correlation, that's different. Correlation is chi-square or correlation analysis. What you got to decide is if they're both quantitative, that means things you can measure, versus qualitative, when somebody says, I like it, I don't like it. Okay? When they're both qualitative, then you use a chi-square. Or there's a combination of qualitative and quantitative, chi-square. Correlation, chi-square. Whereas a correlation analysis is when they're both quantitative, because then you got numbers and you can look backwards. And correlation analysis, I can't remember if I have a picture, no, I don't. It's like, let's say you do this. If all the dots do this, you see that? The line goes that way. That's a negative correlation. And then you decide, is it more than half or fewer than half of the dots follow that line? And you look at it, it looks like more than half. Then your correlation is more than negative 0.5. So remember, it's from 0 to -1 or 0 to 1. So positive correlation goes straight up like that. Negative correlation comes down like this. Okay, then you estimate. If you do that, you'll see there's only one answer on the list. The test writer makes it that way just to see if you know how to interpret this stuff. Okay, so chi-square versus correlation analysis. So qualitative or combination, chi-square. If they're both quantitative, correlation analysis. Or sometimes they'll use linear regression. That's the other one you can use. No, correlation analysis and linear regression are equivalent to be used for quantitative studies. Yeah, there it is, folks. See, only took an hour and 10 minutes, told you. All right, see you in the morning. All right, Mabel, you had a question?